Hi everyone, this is Mrs. G, and today we're going to be simplifying radical and rational exponent expressions. So I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, so go ahead and check your work. When you're simplifying cube root of 24, we notice it's divisible by 8, which is a perfect cube, which is where the 2 came from. 3 goes into 3 once, 3 goes into 5 once, with a remainder of 2, and then 3 goes into 6 2 times. For square root of 1,500, notice that it is divisible by 100, which is a perfect square, so it's 115, and the square root of 100 is 10, which gives us 10 root 15. And then for the last one, it turns out that 2 to the power 5 is 32, so that actually simplifies out. Fifth root of 32 is just 2. And then 5 doesn't go into 4, so the x to the 4th will stay inside. But 5 does go into 9 one time, and then there's 4 remaining exponents. Alright, so here we're going to talk about some of the properties of exponents. I think many of these should be familiar to you guys. So first, the product and the quotient powers of exponents. So to multiply terms with the same base, notice that they do need to have the same base. If you're multiplying terms with the same base, you add the exponents. So notice here we just added x and y. And if you're dividing terms with the same base, we would subtract the exponents. So you can see here again, same base, but we just do x minus y. Now, power of a power, for raising one power to another, we multiply the exponents. So here, notice that we multiplied x and y. To take the power of a product, meaning you're taking the power of 2 or more terms being multiplied, we can actually distribute the exponent. So both parts of the inside of your parentheses get raised to that power, and it's the same for a power of a quotient. We can distribute the exponent. So notice here we have a quotient. We're raising it to the power of x. Both parts are raised to the power of x. One thing I do want to point out is there's no such thing as the power of a sum or difference. What I mean by that is x plus y to the power of 2 is not equal to x squared plus y squared. You cannot distribute exponents when it's a sum or a difference. So I see a lot of people do this. It is completely illegal. So don't do this. So again, there is such thing as a power of a product. If it's being multiplied, you can distribute. If it's being divided, you can distribute the exponent. But if there's a sum or a difference, you cannot distribute the exponent. All right, so now that we've reviewed those powers or those properties of exponents, let's see if we can simplify these expressions using those properties. So for this first one, we have 2 terms with the same base, and they are being multiplied, so we're going to follow our rule, which is to add the exponents. So we just add up 3 over 5 and 7 over 5. So this becomes 25 to the power of 10 over 5. And then this we can simplify. It becomes 25 squared, which is 625. So we were able to use that property to help us simplify. Let's look at part B. So again, I have 2 terms with the same base, and we're dividing. So I keep my base, and I'm going to subtract the exponent. It's always the top exponent minus the bottom exponent. It doesn't matter which one is bigger. It's okay to have a negative exponent. So we're going to do this. So we notice 1/3 minus 2/3. So that leaves us with 8 to the power of negative 1/3. So while it's okay to have a negative exponent as part of our intermediate steps, it's not considered simplified to leave the negative exponent. So remember, a negative exponent does not make your answer negative, it makes it a reciprocal. So this actually becomes 1 over 8 and then it's to the positive 1/3. Now this one we actually can simplify a little bit more if we rewrite it as a radical. Remember, if something is being raised to the 1/3, that's like saying the cube root of 8. And 8 is a perfect cube, so this actually does simplify to 1/2. Okay, let's look at this next example. So here, there's a few different things that we could do to start. The first thing I notice is we have a quotient inside our exponents with the same base. So again, that y has the same base. So let's do that first. So that's going to stay in the numerator, and we say y to the power of, again, since it's a quotient, we're going to subtract. So 4/3 minus 2/3 over 16. The 16 is going to stay in the denominator, and we still have to the power of 3/2. And then let's simplify this. This gives us y to the power of 2/3 over 16, and all of that to the power of 3/2. So remember, when we have a quotient being raised to a power, we can distribute the exponent. And our rule here for raising a power to a power is to multiply the exponents. So we're going to do 2/3 times 3/2, so we multiply the numerators, and then we multiply the denominators, and then we also have 16 to the power of 3/2. Now, of course, here, this just simplifies to y to the power of 1. In our denominator, one thing you might notice is that if we rewrite this as a radical, it would look like this. So this is actually the square root of 16 cubed. Remember, inside out. The 2 we don't write because it's a square root. And we can simplify this. We know that the square root of 16 is 4. And 4 cubed is 64. So this becomes y over 64. So it's always important to look for ways that we can simplify, and a lot of times that will require us to actually rewrite our term as a radical. All right, let's look at this last example. Here we have a product being raised to a power. So here it's really important that both parts of our product, the 27 and the x term, are raised to the power of 2/3. So this becomes 27 to the power of 2/3. And then here, since we're raising a power to a power, again, we multiply the exponents. So 3 times 2 is 6. 4 times 3 is 12. And let's see if we can simplify this at all. So this term, again, we can rewrite this as a radical, becomes the cube root of 27 squared. And then this becomes x to the power of 1/2. We know that the cube root of 27 is 3. So this actually becomes 3 squared, which is 9. And then we can leave this as x to the power of 1/2, or we could write it as the square root of x. Either way, we can't simplify it. So I think either way is fine, or x to the power of 1/2. But please note that we can simplify 27 to the power of 2/3 by rewriting it as a radical. All right, so at this time I'm going to ask you to pause the video and give these two a try, and we will check your answers in just a few seconds. All right, so go ahead and check your work here. In part A, again, here we're multiplying two terms with the same base, so we add up the exponent, so that gives us 12 to the power of 6/3, which is 12 squared. And then here we're raising a power to a power, so we multiply, and it actually ends up giving you 6 over 2, which is 3, and 12 cubed is 1,728. All right, and then in part B, here I distributed the exponent because we have a product, so it's 6 squared, and then x here we have to multiply the exponent, so it becomes x to the 2/3. Notice my denominator stayed the same. And then here I notice we have the same base being divided. So we subtract the exponents. So 6 squared became 36, and then we have x to the power of 2/3 minus 5/3, which gives us x to the power of negative 3/3, which is x to the power of negative 1. So remember, a negative exponent causes your term to flip. And notice I only flipped the term with the negative exponent. 36 stayed where it was, and y stayed where it was. So our final answer is 36 over xy. All right, so now we're going to try simplifying these radical expressions by rewriting them with rational exponents. So we'll see how that can be a useful tool for us. So here we have the 4th root of 9 times the 3rd root, or the cube root of 3. So these are not two things that we could typically multiply. So whenever you have something like this, it's useful to try to rewrite them with rational exponents. So I can rewrite my first term as 9 to the power of 1/4 times 3 to the power of 1/3. Now here, how they're written, we can't multiply them because they don't have the same base. But then if you notice, 9 and 3 are actually closely related. There's actually a way to rewrite 9 to have a base of 3. We can rewrite 9 as 3 squared. So we have 3 squared to the power of 1/4 times 3 to the power of 1/3. And again, we can't always do that, but in this case, we have two numbers that work really well together, and it's ideal for us to have that same base. But let's simplify this first. So remember, raising a power to a power, we multiply. So this becomes 2 over 4, which simplifies to 1/2. So we have 3 to the power of 1/2 times 3 to the power of 1/3. And now, since they have the same base, we can add the exponents. In this, you might need to go to the side to add up those exponents. I'll do it below. Remember, we do need to create a common denominator. So for this first one, we'll want to multiply by 3 over 3. And then we'll want to multiply our second fraction by 2 over 2. So that gives us 3/6 plus 2/6, which is 5/6. So we get 3 to the power of 5/6. Now, a general rule of thumb is that if our problem starts as a radical expression, that's how we should write our answer. So we should take one more step and rewrite this as the 6th root of 3 to the power of 5, 3 to the 5th. And we can leave it as 3 to the 5th, or you could multiply that out. But again, however your problem starts, that's the format we should answer in when possible. All right, so let's look at part B. So here, again, we wouldn't be able to divide these how they look now, because this is a 4th root and this is a 6th root, and you can only divide when the indices, the index here and here, are the same. So let's try rewriting these with rational exponents. So in my numerator, we have 2 to the power of negative 2/4. In our denominator, 2 to the power of negative 9/6. Let's simplify both of those fractions. So 2 to the power of negative 1/2 and 2 to the power of negative 3/2. And now I'm not going to worry about the negative exponents yet because I notice we have two terms with the same base, so we can subtract the exponents. So we have 2 to the power of negative 1/2 minus negative 3/2. So be careful, this actually becomes negative 1/2 plus 3/2. So it's always the numerator minus the denominator. And then this actually gives us 2 to the power of positive 2 over 2, which is just 2 to the power of 1, or 2. So this one actually simplifies really nicely. All right, let's look at this last example. So here, technically we can actually multiply these two radicals together because they are both cube roots. But here we're practicing rewriting with rational exponents, so let's do it a different way. Again, there's different ways we could simplify this. So this x stays the same, and then we have 2y to the power of 1/3, so a product to the power of 1/3. And then here we have 4x squared y squared to the power of 1/3. So here we have another product to the power of 1/3. So you'll notice that both of these products are being raised to the power of 1/3. So we can actually combine it into a giant product, all being raised to the power of 1/3. So we have 2 times 4, which is 8. And then we have x squared, y cubed, all to the power of 1/3. And again, this only works because, one, they have the same exponent, so they're all being raised to that same power, and two, it's completely a product, so 2 times y times 4 times x times y times y. There's no sum or difference. And then here, we can simplify. We're going to distribute this exponent to this product. The x out front is still going to stay the same. So we have x, and then we have times 8 to the power of 1/3. And then here we have x to the power of 2/3. We're going to multiply our exponents, 2 times 1/3. And then here we have y to the power of 3/3, which is just y to the power of 1. And then you'll see here, now I can multiply these two terms. I'm going to add up the exponents. So I'll rewrite this as x to the power of 1. So we're going to add up the exponents. So we have 8 to the power of 1/3, and then we have x to the power of, this is 3/3 plus 2/3 is 5/3, and then we just have y. And now that they're more combined, let's try writing them back as radicals again. So we have the cube root of 8 times the cube root of x to the power of 5 times y, which is not a radical. We know that 8 is a perfect cube, so this becomes 2. Here, we can actually simplify this. 3 goes into 5 one time, so we have x, and then we have y. But notice when we have 3 going into 5, we still have 2 powers of x left over. So this is our most simplified answer. So again, there are different ways we could go about simplifying this, but this is one way we can do it by rewriting these with rational exponents. All right, so at this time, again, I'm going to ask you to pause the video so you can give these two a try on your own, and we'll check your work in just a few seconds. All right, go ahead and check your work here. For part A, when you rewrite them as with rational exponents, then you see, oh, we have the same base, so we can actually subtract the powers. 3/2 minus 2/3, I did that over here, is 5/6. So you have x to the power of 5/6, but again, since we started as a radical, we'll want our final answer to also be a radical to match. For part B, again, I can't multiply these radicals together, so we can rewrite them first with rational exponents. We can simplify 3/6 and 6/4, and then you'll see maybe here you feel a little bit stuck because they don't have the same base, so we can't multiply them if the base isn't the same. But luckily, these three numbers all have something in common. They are all powers of 2. So 16 is actually 2 to the 4th power, 4 is 2 squared, and 8 is 2 cubed. So if I rewrite them like this, then I can use the power to a power property, and I multiply. 4 times 1/2 is 2, 2 times 3/2 is 3, and 3 times 2/3 is 2. So now here they all have the same base, so all you need to do is add up the exponents. So we get 2 to the power of 7, which ends up being 128. So again, it simplifies out really nicely. Again, this only works because these three bases happen to all be powers of 2. If they don't have the same base and you can't rewrite them, it means you can't multiply them together, and that's okay as well. Alright, so now, last thing we're going to do for this video is talk about the properties of nth roots. So the product property of roots tells us that the nth root, so any root of a product, is equal to the product of the roots. So we can take anything that looks like this. If it's a product inside the root, we can actually split it up to two separate roots. That's totally legal. Or we could take two separate roots as long as they have the same index, and we can multiply them together. The same applies for quotients. So again, the nth root of a quotient is equal to the quotient of the nth root. So we can actually rewrite it as two separate radicals if we would like, or if we see this, we can combine it into a single radical. Again, it only works if your index is the same. So nth root, nth root, nth root. So these properties will be really handy when we're trying to simplify our radicals. Alright, so now we're going to see how we can use these properties to help us simplify. So here we have the cube root of 3 times the cube root of 9. So again, our index in each one is the same. So that means we can actually multiply to create a single radical. So we can actually say that this is the cube root of 3 times 9, which is the cube root of 27. And in doing this, we've actually created something that can be simplified more. 27 is a perfect cube. This is just equal to 3. So while I can't simplify them individually, since I was able to multiply them together, it allowed us to simplify more. All right, let's look at this next one. So here we have the fourth root of a quotient. So this might help if we rewrite it as the quotient of 2 fourth roots. We can absolutely split it up like this. And in doing that, that will allow us to at least simplify our numerator. The fourth root of 81 is actually 3. It's a perfect fourth. And then we have the fourth root of x left in our denominator. So here we're going to return to a concept or to a skill that we kind of started learning in the last video, and that's called rationalizing the denominator. So we're going to rationalize. Again, we don't typically leave our final answer with a radical in the denominator, so we need to find a way to clear it. So if I have a fourth root, I'm looking for a group of 4 to make it disappear. So I have 1 power of x, so it'd be nice if I had 3 more powers of x. So I'm going to multiply the denominator by the fourth root of x cubed. So this gives me a group of 4. X times x cubed is x to the 4th. However, you can't just multiply by something in the denominator. We need to multiply by the same thing in the numerator. So our numerator becomes 3 times the fourth root of x cubed. And then this just simplifies to x. And now technically this is a simplified answer. All right, let's have a look at this next example. So again, here I have a square root times a square root. So that means that we can actually multiply the radicands, which is what's on the inside. So 6 times 2 is 12, and then x times x is x squared. Y times y is y squared. And then let's see if we can simplify a little bit more. So again, I'm thinking of perfect squares that 12 are divisible by. So 12 is divisible by 4. That's a perfect square. So it's 4 times 3. The square root of 4 is 2. 2 goes into 2 once, so it simplifies to x. 2 goes into 2 once, so it simplifies to y. And then what we have left on the inside is simply 3. Now technically, when we're taking the positive square root of something, we need to make sure our answer is positive. So technically, we don't know if x and y are positive because they're variables. So if I were being extra picky, I would also ask you to put absolute values around x and y. However, again, this is just if I'm being extra picky. This is fine for our purposes, but just in case you ever see an answer that has absolute values, That's why we want to make sure that our answer is positive. All right, and let's take a look at this last example. This should say example D. Again, here I have two square roots that are being divided, so I can actually turn it into a single square root, 50 over 2, and then I can simplify within. So that gives us the square root of 25, which gives us simply 5. So by rewriting it as a single square root, it allowed us to simplify much easier and quickly. All right, here's our last slide. So again, please pause the video and give these a try on your own, and we will check your answers in just a few seconds. All right, so here we have two square roots, so we can actually multiply the radicals, and in doing so, we get square root of 64, which is just 8. And then here again, we have two cube roots being divided, so we can actually turn it into a single cube root, and then 24 divided by 3 is 8. So cube root of 8 simplifies to 2. So again, this is how we can use our properties of nth roots to help us simplify. All right, so that is all for today's video. Thank you so much for watching.